sponsors and organizers. I'll be presenting some results from our research into the neuroblastoma data. Our focus was a little bit different from the previous talks. We were mainly interested in predicting the exact survival time. So instead of stratifying patients into high risk or low risk, our main goal was to actually model survival times directly. To do that, we used accelerated failure time models. That comes with two challenges. The first, we have to deal with censoring of the data. And secondly, we need to deal with the dimension reduction. We also look at an ensemble method, so it's bagging and rank aggregation that allows us to combine many different models into one, and we'll see if that improves the performance at all. And at the end, we'll look at some results. So we'll actually see that it's pretty difficult to model the survival times, but we can use this to classify patients, and that actually worked out pretty well. So, okay, first some background. So I think we're all familiar with this neuroblastoma. The main thing I'll just say is that prognosis is hard for high-risk groups, right? And that's the theme that we'll come back to at the end. We have a few clinical variables, so age, sex, mycin status. We consider all of those. We have two response, overall survival time and event-free survival time, and both of those come with censored variables as well. This presentation will only look at overall survival, but we have similar results for the event-free survival times. And we also have these other categories, ISS stage, high risk, and favorability. We are only using the RNA sequencing data, so that comes with 28,000 genes, 200,000 transcripts, and 340,000 introns, and we look at all three different levels for that. So ISS stage, high risk, and unfavorable, these are all defined. ISS stage, it looks at the cancer. Has it spread? Where is it spread to? Was surgery successful if it was performed? High risk, this is with patients of stage 4 disease and 18 months age at diagnosis, or any age and stage with mycin amplified tumors. And unfavorable means the patient died from disease despite chemotherapy. And at the end, we'll come back and we'll see if our model can help classify these high risk and unfavorable patients into further subgroups. I think we'll skip this and we'll just get right into the model. So throughout this, I used the original partition of the data into a training and testing set. So everything that we do when we train the model is just on the training set, and then testing is at the end. So accelerated failure time. This is basically just a linear model, and we model the log of survival times. If we're going to compare that to proportional hazards, we can see that right around there, the predictors have a multiplicative effect on time, and that doesn't happen for proportional hazards. So that's why it's called accelerated failure time. But this is the form up here. This is linear model that we'll focus on. So the first challenge is dealing with the right censoring. We did this by an imputation method. So this is a little algorithm that we use, but essentially we first fit the data on the uncensored, fit the model on the uncensored data, and then we use the residuals from that to estimate the distribution of the residuals. We sample from those residuals and then use those to impute the censored observations. And then we have a full data set again, and then refit the model, and we continue like that iteratively. And that's basically all we do. Now we can also, there are other methods, but this is the one that we stuck with. So dimension reduction, there are 4 different techniques we look at. The first one, we try to find latent variables. So this partial least squares, This is just finds some linear combinations of the predictors that explain both the survival time and the variance in the predictors. We have sparse PLS, which adds a L1 regularization to the PLS. We look at lasso and elastic net as well. And all of these are done using tenfold cross-validation. And again, this is on just the training set, so it's tenfold cross-validation within the training set. We also filter the RNA sequencing data. So first we remove any variables with excessive number of zeros. So I picked the threshold 80%. For the genes and transcripts, we also looked at a gene database. We found genes that were associated somehow with neuroblastoma, and we used that data set to further filter these genes and transcripts. And then finally, we looked at how predictive each of the remaining variables are for the survival by just using a single Cox proportional hazards model. We look at the p-values from those, order them, and we ended up picking just the top 2,000 for each of these. So this is what we end up with. We have 5 sets of predictors that we're looking at. 5. The first one, we just look at a model with only clinical predictors. Then we look at genes, transcripts, introns, and transcripts plus introns. Transcripts plus introns just means you concatenate the data sets together. All of those requires the regularization. So there's, in total here, not 21, that's a typo. There should be 4 times these 4 different ones here. Right, we have 4 models for each of those, so 17 altogether. And then we also did the bagging. So for each of these 17 different models, we perform bagging. So what is bagging? The general idea is you just fit several models, you compute performance measures for each one, you choose the best overall performing model, and you keep that one, and then you just repeat. And the way you do this is through the resampling that we use is bootstrap sampling. We again start with that training data set. We have this training data for the bag, and we have this out of bag testing data set. So these would be samples that were not in this training data set. We fit all the models on the training set, this one. We compute all the different performance measures, we rank them, and we get the best one, and then we would just repeat this process. And you can read more about the details in this Shaw et al. Paper. We have 4 different performance measures that we considered. First is just root mean squared error. But the problem with that is it doesn't take into account that we only look at the uncensored variables. So this adjusted version here, it re-rates these residuals with the inverse probability of censoring. So that just takes into account that we are only looking at the uncensored observations when we calculate this. These are both trying to measure the performance of modeling the survival times directly. These last 2, so we anticipated that we might use this for classification as well. So you can use the model to pick a threshold, and if an observation has a predicted survival time below that threshold, we put it in one group, and if it's above, we put it in another group. And we can get some survival curves for that using that method. And we have the long rig test as a statistic to see the performance for 2 different thresholds, 5 years and 2 years. So some results. So this is the root mean squared errors. This first guy here is just clinical variables only. This set here is when you use genes as predictors, and we have 4 different results for each of the 4 regularization methods we use, right? PLS, SPLS, lasso, and elastic net. These are for the transcripts, introns, and the transcripts in the introns. And that last one there is bagging. So from this, it seems like no matter what kind of RNA sequencing data we use, it performs better than the just clinical variables only. But if we look at this adjusted one, it's not so clear. So the midpoints here, these are from the original sample. We got these error bars by doing bootstrapping on the residuals of the testing set, so we could recompute the performance measures and get a sampling distribution of those. And we can see here the errors are pretty large for a lot of these. So it's not really so clear on how these, if these are better than just clinical variables only. And similarly, it's pretty messy for these other ones. But we'll get back to that in a second. So we also looked at the genes that had non-zero coefficients in the models. We looked to see if they were biologically significant, and we saw that they do show up in different pathways. So that was good. Finally, here we're going to use it for classification. So here's a high-risk group. If you just have patients, this is the high-risk survival curve. Here's with clinical variables into our model. And then the idea would be to combine the clinical variable with the high risk and see if we can better classify. And I just clicked on something I shouldn't have. There we go. Okay. And so if we do it with clinical variables in the model, it doesn't really work too well. Right, but that's probably to be expected because the high risk already takes into account the myosin status and the age and all those things. So if we use instead the RNA sequencing data, and here I'm using transcripts and introns with the elastic net, it's actually pretty good, right? We have this set here, this group of, these are pretty bad patients, right? This is like a 2-year survival of 20% or so. So it's able to break off this high-risk group pretty nicely. Similarly with bagging, we have same results here. We can also look at subgroups for the unfavorable. Here's with, again, with transcripts and introns, and we find a group here that's has even worse prognosis. Okay, conclusions. So it was difficult to actually predict exact survival times. I didn't show you much about that, but it was pretty bad. But we were able to use this to improve our high-risk group. So we can divide a high-risk and unfavorable into subgroups and use that for prognosis. Also, bagging and rank aggregation is comparable to the best individual model. Okay, and that's it. I want to thank CAMDA for their travel fellowship. I wouldn't be here without that, and travel award given to me from the Department of Biostatistics at UF. And thank you to Somnath Datta, Susmita Datta, and Alejandro Walker. All right, and if any questions, I think I have time for like maybe one.
Thank you, Tyler. Yes, we have time for a few questions. Any question? Okay. I would have a question. It's nice to see that when you're using the more specific data, like the transcripts and introns, then you're getting better results. But I would like to ask about something else. In the filtering data, at the beginning you were saying that you were removing that 80%. This 80% threshold is taken empirically. It means that were you trying more and less, and then
No.
it was not working, or
No.
it was based on some other.
So that was just chosen arbitrarily,
Okay.
just ad hoc.
Okay, because it will be interesting to see what will happen if you remove less, so you have more these empty points, or if you will just so if you remove less. And when you would remove more, whether this will be like more stable. Right.
Yeah. So really all the filtering was just an ad hoc method. I think at the beginning we tried maybe some other filtering methods, but they didn't really seem to affect. The only thing that affected really was computation time, right? If we had more predictors, it took longer, but the results seemed to be pretty much the same, different filtering.
Any other question? Okay, no. So thank you, Tyler, again. And now we'll switch to the flash talks. The first talk will be by